Hi everyone, I welcome you all in the next lecture of quantum mechanics. So in today's lecture we will see the derivation of the Schrodinger equation. So when we talk about the quantum mechanics, it's one of the most important theories in modern physics, and up to the heart of this theory there lies the Schrodinger equation, this equation that you can see here on the screen. So the Schrodinger equation plays the same role in the quantum mechanics that Newton's law plays in classical mechanics. Newton's law plays in classical mechanics, and then Maxwell's law plays in electromagnetic theory, right? In electromagnetism. So whenever we want to study a quantum mechanical system, whether we are interested in calculating the position, momentum, energy, or overall behavior of microscopic particle, the starting point is always this equation, Schrodinger equation. So this equation allows us to describe how quantum particles evolve and behave under different physical conditions. So here on the screen you can see this is a Schrodinger equation, and this equation is a second order partial differential equation that contains several important quantities. So let's say this h cut is called as h divided by 2 pi, where h is called as the Planck's constant, right? And if we see m is called as the mass of the particle, and then you have x, that is called as the position of the particle, along x-axis, because here I'm interested in doing the derivation for the Schrodinger equation in 1D only, right? Then the most important quantities in this equation is the wave function, that is represented by psi. Psi is called as your wave function, and already I have discussed all the concept related to the wave function in my previous lecture. So if you have not watched that lecture, you just go and watch that lecture and you will understand the phenomena related to the wave function. So the wave function basically contains all the informations about the quantum mechanical system. So once wave function is known, then we can extract the informations like the kinetic energy, or you can say the position of the particle, or linear momentums, so and so forth. So right, so this is what this is the parameters that is there in the Schrodinger equation. But before that, I'll talk about, let's say if we talk about the classical mechanics. In classical mechanics, we study about Newton's second law of motion. And what does it tell us? That if you want to calculate force, that can be equals to mass multiplied with acceleration of the particle, and that can be written as F equals to m d2r divided by dt2. So basically, if we know here the value of r, then from this r we can calculate the velocity of the particle in classical mechanics, that is velocity of the particle is v. Then we can also calculate the trajectories. We can also find out the kinetic energy and various other parameters related to this. So in a way, if we know the value of RT, we can solve for velocity, trajectories, and kinetic energy. So similarly in quantum mechanics as well, solving the Schrodinger equation provides the wave function psi, right? So that is basically a function of x and t, and from wave function we obtain all the physical measurable informations about the particle. However, unlike classical mechanics, quantum mechanical system does not usually quantum mechanics does not usually give exact trajectories Instead, it gives probabilities of finding the particle in different region in a space. So we'll see how we can calculate the probability as well in the next lecture, right? But here, if let's say if I'm talking about for conservative field, for conservative system, if you see, how can we define the v of xt? So if you have force, if you want to define force, then we can write force is equals to minus dv divided by dx, if v is the potential, right? V is the potential or potential energy. Is that clear? Right. So this solution of Schrodinger equation, basically, if you see, solution of Schrodinger equation, that gives you the value of wave function psi xt, and that contains all the informations of particle like position, you can calculate velocity, you can calculate linear momentum, you can calculate kinetic energy, and so on and so forth, all the observables, that is the measurable quantity. But the problem with this wave function is that this is just a physical function, not a mathematical, sorry, this is just a mathematical function, right? So you have to perform some kind of operation. So let's say I have discussed about the kinetic energy operator T cap, linear momentum operator p cap, the position operator x. So we have to perform this operation of this operator over this wave function, and then this wave function gives us all these observable. Is that clear? That's great. Now next thing is that, so if we talk about the Schrodinger equation, and if we apply the Schrodinger equations over the macroscopic particle, that basically leads us to will give you a Newton's second law of motion, F equals to ma. Or sometimes what will happen, if we apply a special theory of relativity, and in constant is velocity is very, very less than c, that is the velocity of light, then it will give you Newton's second law. Is that clear? So it's very important to understand how this is becoming a special case, because Schrodinger equation is a more general concept, and the classical mechanics, that is F equals to ma, Newton's second law of motion, Schrodinger equation will give you, if you apply on the microscopic particle, that gives you the second law of motion. Okay, so right now let's understand some historical development or historical part of this derivation of the Schrodinger's equation. So in 1925, in November 1925, basically what happened, November 1925, Schrodinger was giving a talk on de Broglie hypothesis, right? And this hypothesis basically suggests that the moving particle, so this de Broglie hypothesis basically tells us that moving particle is having wave-like character, right? Moving particle is having wave-like character, right? So this hypothesis, predicted that the wavelength, that is lambda, is in the relation with the momentum of the particle. So if I am talking about lambda, that is called as the wavelength. So since if any particle is having wave-like character, then this wave will be having some wavelength and frequency associated with it. And then there is a momentum. So this wavelength and momentum is in a relationship with each other, right? We'll see how this relationship looks like with the mathematical equation. But right now you have to understand that de Broglie's hypothesis, de Broglie hypothesis says that the moving particle is having wave-like character, and this wavelength associated with the wave is in a relationship with the momentum. right? So when Schrodinger was giving his talk, one of his colleague asked, if moving particles are behaving like a wave, then where is the wave equation? Because if a particle is having wave like character, then definitely there will be wave equation associated with it. And you see, if we have a wave associated with something, there is a wave equation that corresponds to it. And so moving particle is a wave associated with it, then where is the wave equation? And then the Schrodinger took that too hard and went to work. And just after a couple of months, in Zen 2026, Zen 2026, I think this is exactly the 100th year of this particular incident, right? He published a paper, deriving the Schrodinger's equation, and that we have seen here, that this Schrodinger equations look like in this way, and that is what the equation that we are going to derive in today's lecture here, right? So this is all about the historical part of the Schrodinger's equation, that how this de Broglie hypothesis plays a very crucial role in for the derivation of Schrodinger equation. Okay, so as I have already mentioned that if a particle is in motion, then there is that particle is having wave like character, and if wave like character is there, then definitely there will be a wave equation associated with it. So let us suppose a wave equation like del 2y by del x squared, that is equals to 1 upon v square, and let's say this should look like a v 1 upon v square and del 2y by del t square. Is that clear? So let's say I am assuming this equation is my equation first. So this could be the equation of any wave, like vibration or sound or light wave, so on and so forth. So let's say for light wave, if you want to write this equation, this can be written as del 2e by del x square, that is equals to 1 upon c square del 2e by del t square, where c is the velocity of light and e is the energy associated with it. So if you solve this equation, that will give you the solution like E equals to your E naught into exponential minus I, and that is kx minus omega t. So we will see the the parameters associated with this equation all, right? So now if right, so then similarly we can solve this equation as well, del 2y by del x square, that is equals to 1 upon b square del 2y by del t square. And similarly we have the solution of this equation is like y equals to a e to the power I, and that is kx minus omega t. We'll see what is kx, what is omega, and all, what is a. So in complex number, if we have a function like e to the power I theta, you can expand it like cos theta plus iota sine theta, like that. Is that clear? Cos theta plus iota sine theta, like that. Is that clear? So we have to here we'll say for the derivation purpose, you can also expand this above equation like y equals to a, and then cos kx minus omega t plus iota sine kx minus omega t. Is that clear? So we can write this in this way. Great. So this is how we can expand these things now. So we will use these things later on, but here I'll tell you, I mean, there are some assumptions that is there which is associated with it. So we'll start here that first, that the assumption should be like de Broglie hypothesis and Planck's. So this should be consistent, that must be consistent with de Broglie hypothesis and Planck's Einstein postulate. So basically, what do you mean by this point. So as I have told you, there is a wave like character if a particle is in motion. Then if there is a wave, then there is a wavelength associated with that wave, and then we can define lambda, that is the wavelength, that is equals to h divided by p, where h is Planck's constant and p is the momentum. And if I want to define the energy of that wave, that will be equals to h nu, where h is the Planck's constant and nu is the frequency of oscillation. And then we will define a parameter k, that is called as your wave number, and wave number is equals to 2 pi divided by lambda, and here you can say 2 pi into p divided by h, and you can also write p equals to h divided by 2 pi, and here the wavelength can be written as now momentum divided by h cut. H cut is the h divided by 2 pi and p is the linear momentum. Okay, now next is that how next thing is that energy. So energy we have written is h nu, so it can be written as, let's say, h divided by 2 pi, and then I have divided by 2 pi and I'll multiply it with 2 pi. Is that clear? So h divided by 2 pi can be written as h cut, and 2 pi nu can be written as omega. So 2 pi nu is called as the omega. Is that clear? So the energy can be written as h cut into omega. So till now we have got the value of energy is h nu, h omega, and k equals to p by h. So we will use these things in the subsequent derivation. So here we have seen that the Schrodinger equation gives you the solution like psi, if I assume this wave is psi is a function of xt, and that can be written as a e to the power I and kx minus omega t. So that psi of xt can be written as, now we have calculated the value of k, we have calculated the value of omega, that is equals to e by h, and we will substitute this value here. So we will be getting e to the power I by h cut, and then we can write this is px minus et, right? Px minus et. So this is wave for the quantum quantum particles, where the momentum p and energy is e. So this is the wave equation for the quantum particle, right? Okay, great. This is very important thing that we should understand here. So this is the second assumptions, first assumptions. Now we'll talk about the second assumptions for the derivation of the Schrodinger equation. So it follows it should follow the energy conservation. So what do you mean by energy conservation? The total energy E, that will be equals to your kinetic energy plus potential energy, and that E can be written as kinetic energy. Obviously from the classical mechanics we can say that P square divided by 2m plus potential energy V, which will be a function of xt. Is that clear? And for conservative field, already I have told you how can you calculate the potential energy. If you have F, and F can be written as minus dV divided by dx. This is how you calculate the F if you know the potential or the potential energy. Is that clear? Now third postulate will be the principle of linearity. Principle of linearity or superposition. Right, so here if you have a wave function psi 1 and another wave function is psi 2, and if I want to write a resulting wave function psi, that can be written as linear combination of c1 psi 1, linear combination of psi 1 and psi 2. So I can write psi will be equals to c1 psi 1 plus c2 psi 2. Psi will be equals to c1 psi 1 plus c2 psi 2, and this is also called as the superposition of two waves, that is psi 1 and psi 2. And then fourth postulate is if you have force, that is equals to minus dV by dx, and if V is constant, or if potential or potential energy is constant, then in that system force will be 0, and that is called as the conservative system. Right, next coming to the next point, that we have got that psi of xt, that is equals to a e to the power I divided by h cap, and px minus et. Px minus et. Is that clear? So I'll do del psi by del x here. So I'll write a, this is just a simple derivation. E to the power just simple algebra you have to perform here, calculus. I by h px minus et, and then there will be multiplication of I by h cut. Only simple differentiation is there. Then I'll differentiate 2 times del 2 psi by del x square, that is equals to, again I'll differentiate this, AP square, it will give you I square divided by h cut square e to the power I divided by h cut, and then it will give you px minus et. Is that clear? So if you see the above thing, what is this? So a and e to the power px minus et, that is equals to psi. So basically I square is minus 1, so I square will be give you minus 1, and what is psi? Psi is equals to a e to the power I px minus et. Is that clear? I by h px minus et. So basically what do you mean by this? So the value of del 2 psi by del x square, that will give you minus p square divided by h square psi. So let's say I am assuming this is my equation 4th, right? Or later on I'll put this thing. So basically what you will see here, so the value of p square psi, that can be written as minus h square del 2 psi by del x square. Is that clear? Let's say assuming this one is my equation first here. Right, now if I want to perform this, so we know the value of psi, that is equals to a e to the power minus I by h cut and px minus et. So if I perform del psi by del t, it's as simple as that. We will be getting minus ae I by h cut and e to the power I by h cut, and then obviously px minus et. Okay, so if you see here a and e to the power I by h cut px minus et, so it can be written as del psi by del t, that can be written as minus I by h, and then it will be equals to e psi. So if I want to calculate the value of e psi from here, that will be equals to minus h cut divided by I del psi by del t. So that will be equals to I h cut del psi by del t. So let's say this is my equation second. And now what will happen, applying first and second in conservative principle. So basically what we have seen, that this total energy was equals to p square divided by 2m plus v. So if I operate this psi over here, psi and psi, so what we will get, that we will be getting E psi, that is equals to p square divided by 2m psi plus v psi. Is that clear? And we have calculated the value of E psi here, that is minus IH, that can be written as minus IH del psi by del t, that is equals to, what is p square by 2m? So p square psi is equals to minus h square del 2 psi by del x square. So p square is minus, so that can be written as minus h square divided by 2m, and then definitely del 2 psi by del x square, plus it can be written as it is v psi. Is that clear? So from above hypothesis, we have calculated this value and this value, and finally this is the equation that you can see here. This is the final time dependent Schrodinger wave equation that we have derived from various hypotheses. So this is called as the time dependent Schrodinger wave equation, right? Okay, great. So this is all about the derivation of Schrodinger wave equation. In the next lecture, I'll be talking about how to solve the Schrodinger wave equation for various kind of system, and in subsequent lecture we'll be talking about Born statistical interpretation and the normalization of wave function. And also after that I'll be talking about particle in a box, that is in one dimensional and two dimensional thing, and there you will actually see the the application of the Schrodinger equation. Okay, so thank you all for attending this lecture. See you in the next lecture where I'll be talking about the solution of this Schrodinger wave equation. Okay, thank you.